So welcome everyone to the 5th session of the Python Bootcamp. And thank you for attending. I'm going to share desktop 2 here, and can I get confirmation that we are all seeing the title slide, inheritance and composition? Thank you, Michael. Okay, so, and Robert. So today's topic is essentially part 2 of object-oriented programming, and we'll see pieces of code that are very familiar from Monday. Everything we talked about on that day, specifically how to create classes and give them properties and functions, is going to be the most relevant information today. And so without further ado, let's just start with a simple definition of what we mean when we say inheritance and what we mean when we say composition. Inheritance is the principle of basing an object on another object. And this is a very efficient tool in programming because the properties and functions that classes have are automatically implemented in a new class when you inherit from another one. So this is essentially in the vein of not writing the same code multiple times for a set of connected objects. And, rather than implementing, say, 5 or 6 objects that all share more or less common features, rather than implementing 5 or 6 objects all with the same property functions and the same functions, you can set up some inheritance structure so that you don't have to do that. And in the end, your code will actually be shorter than the case where you didn't have an inheritance structure. The idea and some of the jargon with this, the idea is that a subclass, which may also be referred to as a quote derived class, inherits from its parent class. And the parent class may have its own parent class. It may also inherit from some abstract object, which may be coded by you, the user, or some external library, or it may be a Python built-in value. It just needs to be an object. That's the only prerequisite. Composition, on the other hand, refers to when an object contains other objects. Is the root here, composition, means the object is composed of other objects, hence the term composition. So you have something which is made of other things, and sometimes it may have meaning without them, and sometimes it may not. And a good example of this would be, say, cars with wheels. Cars have 4 wheels, but a wheel and a car may be 2 different objects that you create. And every car should have, if it's, unless you're talking about like a semi or something, or some very large vehicle, your car is going to have 4 wheels. And without those 4 wheels, you're not really going to go very far. So let's start with inheritance. A good example of inheritance, which is relatively intuitive, but the implementation of which I will leave for an exercise for today, is pets. What you could do is implement a base class pet, and then let cat and dog inherit from pet, and then you can have different breeds of cat or different breeds of dog, which inherit from cat and dog as they should. This is a very powerful use in Python, and the example of this is that features which all pets should share can be implemented in the pet class, in the base class for this set of objects, and those features then will be automatically shared by all of these subclasses, and you don't have to rewrite them. In fact, if you rewrite them, that's called overriding, and we'll get to that in a second. Then just like features which are shared by all pets, features which are shared by all cats and all dogs will be implemented in the cat class or the dog class, depending on which animal you're talking about. So another example, which is very similar to this, so you can, in doing the exercises for today, you can somewhat base your implementation of a few of these pet classes off of what we're about to show, is students and professors. So if you're going to implement a student object in Python and a professor object in Python, it makes sense to have them both inherit from a class which is just a person. And in that class, you can store properties, features, really anything, which are sort of universal. So depending on whether or not a person is a student or a professor, you know that the person is going to have a name. So you can give the person class a property name. And so far, nothing here is new. We've just made an object. This should look very familiar given what we've done on Monday. And to review, we just simply declare the class. We have an initialization function here, which has this special name, init, which has 2 underscores on the beginning and end of it. And it should always take self as the first argument, and any subsequent arguments that thereafter. And so it takes in the name of the person. So then it calls the setter function, this self.name equals construction will always call your setter function here. If we need to review on this, I will refer you to the slides and recording of Monday's session. But just to reiterate some of what goes on here, this just checks to see that the name is a string first. It assigns it to and then it assigns some name under the hood for it to store, and it capitalizes that name. This capitalized function is just a function which runs on strings, which capitalizes the first letter of their name if it wasn't already. And otherwise, it just throws some error and says their name has to be a string. And all this property does then is when you have some object which is an instance of this class, you can just say like, person.name, and it will return what is stored here. So far this is not new material from at least not from our last session, but nonetheless you need some construction like this in order to start an inheritance structure, because you need a class to inherit something from. So extending this then, if we want to implement a student in Python, we change the declaration of the class slightly. Specifically, we specify which class it inherits from in parentheses immediately following the name of the derived class. So here we're making a subclass or a derived class. Those really refer to the same thing. And we're making one of these which inherits from person. And all we need to do is take in the name of the person as an argument, and then we have to call what is known as super. Super is a keyword in Python, which will always refer to the parent class. So in this case, person. So what this does then is it initializes a person object, and in that it first calls the parent class to initialize the parent class. And what that does is this is when it creates the name property. The init function, which we saw on the previous slide, is what is called, this function right here is what is called by this line right here. There's a question in the chat. It says, does the student class have to be in the body of the person class, or is it standalone? It is standalone, actually. So this, it may be hard to see, but this right here, where the grayscale changes slightly, where my mouse is, that is the leftmost edge of my text editor. So this is actually, this class student declaration was not indented at all. The fact that the student class does not have to be in the body of the person class is nice as well, because then if you have classes which are rather large in implementation, you can put them in separate files. So I could say import the person class and then subclass it here like so, and it wouldn't have to even be in the same file. So to see this in action, this import statement just comes from the fact that this is in a file named people.py, and I was in that directory when I made this example code. So this is in the GitHub repository under examples /classes/people.py, and I just dropped that into the chat window. And all of the person class and each of the subclasses we'll see here in this set of slides are implemented in that file, so they're all in one place. We could have put them in multiple files to show you what that would look like, but this is in this case just shown in one file. So it's a relatively short example. So this import statement, when I say from people import student, the people refers to the people.py file that I wrote, and then student refers to the class here. And what I've done is I've just made two instances of it, Mike and Peggy, and their names are as you would expect. And they have this .name attribute. So I can say Mike.name, and it gives me his name with the first letter capitalized as we wrote, and same for Peggy. One thing to highlight is the isInstance function, which is particularly useful in checking that variables are of a given type, and this is useful in doing, say, like error handling in your classes. Mike and Peggy, or sorry, Mike, and this is also true of Peggy, but Mike is an instance of both the person and student class. So he is specifically an instance of the student object, but he is also an instance of the person object because student inherits from person. So when you evaluate an isInstance function, it evaluates to true not only if an object is an instance of a given class, but if it is an instance of a derived class of that object. So hence this true, this return value of true here. Mike is a person object because he is an instance of a class which inherits from person. So to extend this, the derived class, it can have anything that the base class doesn't. So to show this, I've given the student class a function called work, which just prints the message, some string is working on the assignment, and for that string, I stick in the value of their name. So it just prints, so-and-so is working on the assignment, and that is unique to the student object. And so to illustrate that is unique to the student object, I import from this file again, and I import both the person and the student classes. I construct Mike as an instance of the student class, and Peggy is now, rather than a student, she is an instance of the person class, but she is not a student here. So when I call Mike.work, it prints this message, Mike is working on the assignment, just as this function should. But when I call Peggy.work, it raises this attribute error and says it has no attribute work. So Mike, being of the student class, has this function work, but Peggy, being an instance of a class which does not have that function, the behavior is exactly as you would expect in that case. You get some error saying, hey, I don't have a function called work. So this is an instance of, say, extending one class to have functionality which is not which is not included in another. The second derived class would be the professor. So we, again, just like in the student class, we have our init function, and we call the init function for the parent class, and we give it the name which was passed. And this is what creates the name property for each of the derived classes to inherit. And we give the professor a function which is also called work, but now rather than saying that that this person is working on the assignment, it's the professor's job to grade the assignment. If you're a grad student, you know that there's an asterisk on that. Oftentimes it's the grad student that grades the assignment, but we won't split hairs here. We'll say that it's the professor who's grading the assignment. So just like before, this just says some string is grading the assignments, and it sticks their name in for that string and just prints to the console. And to show this now, we're again importing from this people.py file, and we pull in the student and the professor object. We make Mike and Peggy. Just like before, Mike is still the student, but now Peggy is the professor. And when I call their work function, I say Mike.work and Peggy.work. It prints Mike is working on the assignment, and it prints Peggy is grading the assignment, just as we intended. So this is another instance of giving two similar yet slightly different objects common features, like they both have a name property, but they have two different functions called work. And so this is a very powerful construction, because you can let objects share properties by letting them inherit from a base class, but then you can give them functions which have the same name but execute a different task based on what subclass they are. So this can be very powerful in research by letting say two different objects which may be similar. You can give them the same function but have those functions do slightly different things if they have to. So the next example is what would happen if we now give the person base class a function called work. And what happens now is rather than the student and person classes inheriting this function, they have now overridden that function. So if I were to go into the students and professor classes and remove their functions which say work, they would inherit this, and it would still run now with this print statement. But I haven't done that here for example purposes. What this function does is if a person object is an instance of the base class person, when you call their work function, it just prints the message that they are on the clock earning a paycheck, and you stick their name in for that string. So this would be like assuming some default scenario where the person is not a student or a professor, and so by default we would just assume that they're not in academia, that they're working, say, in the private sector. So their job is there at some business doing their part and earning their paycheck. So we have an additional person now. We first import from the people.py file again, and this time we pull in the person base class and both the student and professor derived classes. And Mike and Peggy, just like before, are the student and the professor. And we now make Kelly, who is just a person who we let have the default behavior of being not someone who is working in academia. So then when we call the work function on each of them, they all have this function, but they all do slightly different things. It says that Mike is working on the assignment, Peggy is grading the assignments, and Kelly is on the clock earning her paycheck. So this is a way to give a set of objects which are all related, functions with the same name, the same call signature, but doing different things under the hood and performing different tasks and executing different tasks because because it makes sense for that object to do that a little differently. It is so. So before I go on, I'll say the next few slides focus on subclassing of built-in data types. So I want to pause now before we hit it and take 10 seconds or so and ask and take questions if anyone is confused about anything that's going on here. All right. If we don't have any questions, we'll go ahead and move on. This is it for the students and professors example. So the next few slides are about subclassing built-in data types. This is specifically to call out that you can subclass built-in data types. So remember, and this is going to come up yet again in a few minutes, remember the Python data model, which is that everything is an object, integers, floats, functions, everything. Because they are objects, then you can subclass them as well. You can subclass integer, you can subclass float, you can subclass dictionary, you can subclass list. These are all subclassable things. Everything is subclassable in Python because everything is an object. So the advantage to this is inheriting built-in features can be extremely powerful, allowing, if you were to subclass float, your object would have some new feature that you give it, but it would also inherit all of the built-in features that float objects normally have, like mathematical operations and such. The downside is that this can be a little difficult to get to set up because oftentimes the built-in types accept an arbitrary number of arguments or keyword arguments, as we discussed last week when we were talking about Python documentation. So just a fair warning: if you want to subclass a built-in data type, it is good practice to first read the documentation on the built-in data type extremely closely, so that you are aware how to construct these objects and how to create them and what types of features they will inherit. That in a lot of cases that will be relatively obvious given what you are subclassing. Like if I am subclassing a float, obviously I'm going to inherit a lot of numerics behavior. But nonetheless, the functions and attributes which you inherit may not be quite so obvious to you. So as an example of this, I will here subclass a list to make it a very simple array object. And I'll show you what this looks like, and I'll break down this example code. The arrays differ from list in that all of the elements of the array should be of the same data type. This is one of the distinguishing factors between lists and arrays. And sure, there is a built-in array object. So this subclass would be pretty much superfluous. It would not be necessary to do this, but nonetheless, it can be enlightening to see how you can emulate this functionality by subclassing list. So the task is rather simple. We need to make a list, and what we need to do is have it somehow track the data types that the user is desiring the extended list into an array. This simple array object, we need to specify the data type and tell it what type of object each element should be. So the first step with any class is to write first to declare the class and to write the init function. So we declare our class and we give it some name, and here I've just called it simple array, and we're subclassing from list. So list has to go in parentheses immediately following simple array, followed by a colon. And the init function for list takes an arbitrary number of arguments and an arbitrary number of keyword arguments. So that is declared explicitly in this init function. And recall from last week that that when you pass objects as parameters with this construction, this first asterisk before args turns this object into a tuple with some unknown length. And in that tuple will be all of the positional arguments that the user has specified. And the keyword arguments here, the two asterisks followed by KW args, turns keyword arguments into a dictionary. So the keyword arguments, all of the keywords that are specified will be the keys of the dictionary and what they are assigned to as the values. So we're not declaring or accessing these arguments or keyword arguments directly. Instead, I have a simple if statement here to detect a given data type as a keyword argument called dtype. So this says if dtype in keyword args.keys. So that says if, that's basically saying if the user has specified a data type for this simple array object, then it goes ahead and assigns self._dtype as an attribute to what the user has specified. And then it removes it from that dictionary. That's what the del keyword here does, is it removes the key dtype and its value from that dictionary. So it is no longer present in the dictionary that was constructed out of the keyword arguments. Otherwise, if the user did not specify a data type, it assigns it to a particular type called object. And we'll come back to this in a few slides. This is essentially, object is a keyword which refers to just any generic object in Python. It could be int, could be float, could be list, could be anything, and that's just this is just the generic Python object-based class. The next step, after knowing that you have a data type assigned, it then checks to make sure that every element of the list which was passed, which is args0, first element of the arguments passed, that is what you are that is the list that you are constructing into a simple array. It makes sure that they are an instance of the data type. And if so, it then calls super, which is list, and gives it all of the arguments and keyword arguments that were passed, minus the data type since you removed it. And if not all of the elements are of the specified type, it just raises a type error as it should. That should produce an error. If we give this function, or sorry, if we give this object a list to construct an array out of, which does not obey the data type you specified, that should raise an error. So that's exactly what we do right here. The next thing to override is item assignment. Remember that item assignment proceeds according to the magic method set item. So you write a function with the def statement with 2 leading underscores, set item, and then 2 following underscores. And then it needs to take self as the first argument, some key or index as the second, and the value to assign as the final argument. And then we'll always proceed in that order. And all this does is it says, hey, if the value I got is an instance of the data type that this array stores, then call super and call its set item function and give it the key and value that were stored. Otherwise, if the value is not of the given data type, raise your type error and say that this has to be of that type. And what these string specifiers do is just tell you that data type was and what it got as the value to assign. And then we just give it the property method d type, so that you can say simple array dot d type without the underscore, and it will find the value which is stored. So I want to call out specifically the reappearance of super in the set item function right here. Super does not only occur in the init function. It can be used anywhere you need it to refer to the parent class. So in this way, there is the simple array object has its own set item function, which overrides the inherited set item function from list, but it can still refer to the inherited version, which is not overridden by simply calling super, and then with a dot and underscore underscore set item underscore underscore, it can call this function and simply pass it up the ladder to its parent class. So these notes I've made here on the left, the type error is raised by the initialization function if all of the elements are not of the given data type, and the set item function then ensures that any value you assign thereafter is indeed of the data type which is specified. And again, super is used to refer to the parent class always, and that can happen anywhere. It doesn't have to happen in a magic method. It doesn't have to happen in initialization. It can happen in a property. It can happen in a setter function. It can happen in any generic function, you name it. So to see this then in action, I just make a simple array object with the list 0, 1, 2, and I specify d type equals int. And just give it the integer type specifier as a keyword argument. So I didn't give this function a string representation. This is inherited from the list. This is exactly what a list would look like otherwise. I didn't give it a get item function either, but yet item access proceeds just as it does with a list because that functionality is inherited. I can assign a given index to a given value. Here I'm saying the 0th element is now not 0 anymore. Now it's 1, and so I have 1, 1, 2.
Have fun. Good luck.
As
Sorry.
my list. No worries, Rachel. So then this passes. This line right here passes because 1 is an integer. So if I try to give it 1.1, it then finds exactly the error that I raised earlier. It found that 1 is not an instance of self.dtype, or sorry, 1.1 is not an instance of self.dtype here, which is a float, or sorry, integer. So 1.1 is a float rather than an integer. So that if statement right here evaluates to false, and the set item function, which is what is called when you do this type of item assignment, finds that type error that we implemented, and that is essentially how you would emulate the properties of an array using a list. You would subclass it and override the inherited features until you have the features that you want. You can also create, with this exact same process, only even less work, even fewer lines, you can subclass exceptions and warnings too, to make your own error classes and your own warning class. So if you haven't seen it before, the warnings module is the Python standard library. You don't have to install anything to get the warnings module. If you have Python, you have the warnings module. And that is how warnings are raised. If you want to make a new error class, you should subclass from exception And if you want to make a new warning class, you should subclass from warning. And these have exception with a capital E and warning with a capital W. And unless you want to do something special, you don't actually need to do anything. You can just put a pass statement in here. And in case anyone hasn't seen this before, pass is a Python keyword, which means just do nothing. There doesn't need to be anything there. If I did not have this pass statement here, you'd get some error. It would, for one, if I ran this in IPython, I would keep hitting enter, and it would continue to expect me to give something here, because there's a colon here denoting that this will expect some indented block. So if you want this to do nothing, you can just have an indented block that just says pass. And what this does then is if I raise a custom error, which is this class that inherits from exception, and I give it some message, my custom error class, some example string to raise along with the error, it raises it just like you would expect. The name of your error pops up here, color-coded in IPython as you would expect, and the message along with it. And you can do your custom warning class in exactly the same way. You can say warnings.warn. It takes in some string message, and then the warning class itself, which is custom warning. And then you can see here that this prints with the console the type of warning that should be raised. So the reason you don't have to give these classes an init function is that you can let them inherit the init function. So if one thing I didn't mention, which was somewhat sleight of hand, is in let's say the student inherited class here. This init function is actually unnecessary. If all you are going to do is call super, if that is all you're going to do, you don't actually need to write the init function because it will inherit. You can then let it inherit the init function from the parent class. So the init function is not special in that regard, in that you can let it get inherited by the parent class from the parent class too. So to call this out specifically, it's not that these two classes don't have an init function, it's that they inherit the init function from the exception class, from the warning class. So the call to super is actually superfluous. Nonetheless, for stylistic reasons, some people don't like classes that don't have an init function, so they will put one in there anyway. That's up to you as a programmer. You have the full discretion to do that. So I promised last week that on several instances, we would kind of circle back to some of the things that I told you in the first few sets of slides. So I want to specifically call out here the Python model, which is this statement that I brought up earlier, which is that everything is an object in Python. And what that means is that at the end of the day, everything inherits from object. So what that means then is the isInstance function for some Python variable with object as the second keyword will always return true. Everything is an instance of object. And so what that implies, to see this in action, I can say if is 3 an object, that's true. Is some string an object, that's true. I can even import NumPy and ask, is NumPy an object? That's true. The entire NumPy module is also an object. The list 0, 1, 2, is that an object? That is also true. This is now seeing one of the first things I told you guys in action. Everything inherits from object, and that is how the Python model is, and the data model of the Python language is implemented into this coding language. So that is why when I have this subclass list, I assign the data type equal to object. If I just say I don't specify, if the user does not specify the data type, then what this does is it lets anything be assigned to that array. So then this is instance I object will always evaluate to true, and anything can be assigned anything can then be assigned to this simple array if the data type is an object. It can be strings, it can be floats, integers, other lists, anything. That is the end of the first half of this set of slides. Let's take some questions now, and the rest of these slides focus on composition rather than inheritance. So once we're done with questions, I would propose we take the 5-minute break, and we will resume then with composition when that 5-minute break is done. So, are there any questions on inheritance thus far? All right. Well, if there aren't any questions on inheritance, then I say let's go ahead and take the 5-minute break. One thing I do want to say before we break, just a couple quick notes. There have been some updates to the Git repository, to the slides and exercises. So just to remind everyone, you should use the cd command to get to the directory where you cloned the repository or downloaded it. So that's the cd command to get to that directory, and then you just run git pull, git with an I, and I've just placed that in the chat. That will download all of the updates for you automatically. And another thing to say is that this bootcamp by nature progresses relatively quickly, and that is by construction because there's a relatively wide range of skill sets that each of you have. So if some of this object-oriented programming stuff is still a little abstract to you, don't worry. Just keep working on the exercises. Keep asking yourself how you might apply these things in research, and over time with practice, they will become much simpler to you. So if this is on the more difficult side for you, do not fret. So with that, let's go ahead and take our 5-minute break. I will stop the screen share briefly so that I can pause the recording. 2, 1. We are recording now. So I will go ahead and share my screen once again. And can I get a quick confirmation in the chat or verbally that we are again seeing the recall the Python model slide? Thank you for multiple of you. Thank you. So as promised, the rest of these slides focus on composition. So I will just flash back quick to the second slide. Remind everyone that composition, as opposed to inheritance, where inheritance was the case where an object is based on another object, or maybe some kind of extension of its parent class. Composition is instead the case where an object is composed of or made of, contains other objects, and may not have any meaning or useful application without the object that it is composed of. So without further ado, I constructed a very astronomical example to this, and what we'll see here is a solar system. A solar system has a star, it has planets, moons, asteroids, comets. There are other things in solar systems. There may even be 2 stars in the solar system, but for this case, we'll just assume that this is a solar system which is somewhat like our own in that it has a central star, it has planets orbiting that single central star, and those planets may have moons, and then there are also asteroids and comets flying around. So in this example of composition, I will also make use of an inheritance structure. And so this is the basic schematic of what this is going to look like, where every object I just listed is going to in some way inherit from the base class body. And there's first just a generic solar system body, and then a subclass of that is the star, and a subclass of that is the satellite object. And then the planet, moon, asteroid, and comet inherit from satellite in the sense that these are all specific types of satellites which orbit the star, or in the case of a moon, its host planet. Then these black boxes indicate where we'll make use of composition. We can construct a planetary system object composed of a planet and its moons. And we can construct a solar system object composed of all of these objects. Composition, unlike inheritance, doesn't require any new special syntax, and we'll see this in a second. But first, we have to have a place to start. So we are implementing an inheritance structure first for all of these objects to live in. So the first piece is the base class body, which star and satellite are going to inherit from. So here is that base class. And this structure is very similar to what we saw on Monday. We just have the class declaration. We have an init function, which takes in a name and a mass, and it just calls the setter functions, and it gives the solar system body a name, which must be a string, and a mass, which must be a number. So not pictured in this example code is the import numbers statement, which lets me access the numbers.number data type. So what that means then is the star and satellite and all derived classes will also have a property called name and a property called mass. And name is guaranteed to be a string, and mass is guaranteed to be a number. If I wanted to complicate this and be a little more specific, I could also require that this value, which I'm assigning the mass to, be non-negative. Rather, I could have some if value greater than or equal to 0 check, and then assign the mass. That would be some sort of like sanity check on the value that is given to the setter function. So if a star doesn't need anything else, we can write the simplest inheritance scenario that there ever was, which is just the class declaration and a pass statement. So remember, pass is this Python keyword which just says do nothing, and so what this does is star looks just like the body class. It inherits the init function. And so you can create a star object with name and mass, and it will just simply call this function directly, which it inherits, and it constructs these properties automatically. And yet the star object has essentially 0 source code. It's just 2 lines, very simple. So then we want to construct a satellite object, and now this is a slightly more complicated version of the body scenario. This init function here, I have it directly after the satellite declaration. It takes in a name, a mass, and we're also going to let these satellites track their semi-major axis and eccentricity. And here I've got semi-major axis as a positional argument, but eccentricity as a keyword argument, in that I have declared this eccentricity equals 0. So the user doesn't have to specify that, but So it first calls its parent class. It initializes the parent class with the name and mass properties, and then it constructs its own semi-major axis and eccentricity properties. So it calls these setter functions, which ensure that the semi-major axis is a number which is itself greater than 0, and otherwise raises a type error saying it needs to be positive, or says that it needs to be a real number and got something else. And eccentricity itself has to be a number and must be between 0 and 1, and otherwise it is either a value error because the value it got was not within that allowed range of 0 and 1, or the eccentricity was just not a number to begin with. So this is more or less the same principles as went into the body base class here, in that we have a property function and 2 setter functions to go along with, except now they're just 2 different properties. One's the semi-major axis and one is the eccentricity. The satellite subclasses then, if we're not going to give them any extra data, we don't need to, and we don't need to write anything within the body of those classes. So a planet can inherit everything from the satellite, and so can the moon, the asteroid, and the comet. If you're using some construction like this for research, you may find that you do need to give the planet object more data, in which case then you can give it its own init function or its own new properties and setter functions. And the same with the moon and the asteroid and the comet. But here, for this example, if we're not going to have them be axis and eccentricity, then we can simply let them inherit those properties and setter functions, and we don't need to write any additional code. We just simply declare the class, say pass, and move on, and everything is automatically inherited. So now getting into the actual composition side of things, this, with a pretty straightforward approach, composition is achieved as I promised. There's essentially no new syntax. All we're doing is letting the objects that the planetary system is composed of be the properties of your class. So here we have a planetary system object, which is composed of a singular planet and moons. So the planet attribute is just simply the planet object itself, and the moons is a list of the moon objects. So the setter functions are relatively straightforward. Note that this doesn't inherit from anything. This is now a base class, hence the lack of parentheses with some new data type inside. So it does require an init function, and we have a planet as arguments, which then call these setter functions, and we say, okay, if the value passed to the planet setter function is an instance of planet, then we assign it. Otherwise, we raise a type error and say this needs to be. We then check, is this value that was passed a list? And if so, is every piece it contains, every element within that list, is it an instant object? And if so, then we copy it into the moon's attribute. Otherwise, we raise a type error saying they all have to be a moon, or maybe we didn't get a list in the first place, in which case that would also be a type error. So this is no new syntax. We're just applying it a little differently, saying that this property planet has to be of a type which I implemented, as opposed to a type which is built in. And then the moon's object is an instance of a built-in type, but the elements of this list are instances of a class which is moon class. So this is how you achieve composition. Nothing new, just a slightly different application of what we've already seen. The solar system object then proceeds similar. We have a star object now, and it takes in a star, the planets, the asteroids, and the comets as arguments. In the init function, we call all of these setter functions. The star checks that the value which is passed to it is the star, else it raises a type error. For the sake of remaining concise, I have left the planets, asteroid, and comet setter functions actually off of this because they proceed essentially the same way as we've already seen. It checks to see that the planets here are instances of the planetary. It expects a list, just like the moon's setter function here. There is a function in this class which says planets.setter, and it checks to see that the value that was passed to it is a list, and then all of those elements are planetary system objects. Same with asteroids and comets. It checks to see that those are lists, and then it checks to see that each of their content are asteroid objects and comet objects, and if so, copies them into the properties. So this, again, even in the solar system object, no new syntax. It's just properties of a very specific type, and that's all you need to achieve composition. So here's the planets object to show that one, so that you can see maybe in a little more clarity what the subsequent two look like. There's this first is instance check to see that the value was a list, and then it checks to see if each of the elements of that list are planetary system objects, and if so, it assigns the attribute. And the asteroid and comet setter functions are essentially exactly the same, just with a different type right here and a different name of the function. So to see this in action, to see the kind of things you can construct with this, I have imported this file into IPython. So to show each of you this where this is at, I'm putting in the chat now. This is at examples /solar_system.py. I just place that in the chat. So that file is there for each of you as an example of how you can use composition, but also inherit. Here is I have simply composed some of the objects within the solar system to construct our own solar system as an object within this The star, its name, we just give it sun, and the mass in solar masses is 1 by definition. That I then make the Earth, which is about 3 parts per million of the sun by mass, and the semi-major action. And here I'm not specifying an eccentricity, I'm just letting the eccentricities be 0. So I then make our own moon and Mars and its 2 moons, Phobos and Deimos, as instances of the same framework of objects in the same units, and these are just planet and moon objects that are found within file. I can then make the Earth-Moon system, and this is where composition now enters. It expects a planet object and a list of, so I give it Earth, which I just created right up here, and I give it a list containing only one element, our moon, and that was created right up here. Mars then expects obviously a different planet. It expects Mars instead of Earth. So I give it Mars. And for the list of moons, it's now a two-element list, Phobos and Deimos, which were created right up here. So we can then create our solar system by passing each of the Sun, the Earth-Moon system, and the Mars-Phobos-Deimos system as now arguments equals solar system dot solar system. And so this name is as it is because this refers to the file which I imported before the dot, and this after the dot refers to the name of the class. They just happen to be the same. So this is module or file name, whatever it is alias to, and then dot, and then the class name, and they just happen to both be solar_system. And the argument it took, as shown by this class here, was the star, the planets, the asteroids, and the comets in that order. And I've given it our Sun, a list containing the Earth-Moon system and the Mars system. And I've just, for the sake of being concise, I've just neglected to specify any asteroids or comets. These are, this is not a special character. These are two square brackets back and forth, which is just declaring an empty list. I'm just saying, for this example, we're not tracking the asteroids and comets. So what you can do then to access the data that is now stored in your composition constructed solar system is our solar system dot star accesses the property star, and then dot name accesses its property name, and that's the Sun. Then the planets is a list, but you can still access its the properties, the elements of that list very concisely. Value, access the planet itself and then the name of that planet, and we find Earth. The planetary system also has moons. So you can say the 0th planet and its 0th moon and the name of that moon. Here we gave Luna. That's the name that I have adopted for our moon. Then I can also look at the first planet and its planet, the first planetary system rather, and then the planet in that planetary system and its name, and it is Mars. Then the same thing of that planetary system and find their name, and I find Phobos and Deimos. And then I access the asteroids and comets objects, and we find that they're just empty lists. So this is organized data. You can construct objects which are composed of other objects, and then access all of those properties using just nested versions of this construction, which we've been using in the exercises from Monday, where you can just say, our solar system dot star dot name, our solar system dot planets, give it some index dot planet dot name, and you're just accessing properties, properties of properties, and so on until you find what you are looking for. And so this is a way you can set up a nice organizational structure to a given class. That is it for this example, and this is the final slide for composition. So this is just a final note, which is somewhat in the abstract, but I'm calling it out just for the sake of calling it out. In talking about these topics, you might find some people differentiating between composition and aggregation, which are extremely similar, but are different in one key aspect. And so this is just to make all of you aware that you might hear the term aggregation as opposed to composition, which is their point. A case where composition is employed is when one object essentially owns another, and that's where, and that is what we saw in our example. The solar system object owned the planetary system object, and the planetary system object owned the planet and the moon objects that were properties of that class. Whereas if an object simply used another one, then that is aggregation. Specifically, if a given object is destroyed when you destroy a given class, that's composition. But if I were to destroy a class which did not get rid of one of its components, then that is aggregation. So the reason we are using the reason that these previous slides were composition and not aggregation is simply that the planetary system object had the planet as a property and the moons as a property. Whereas if these were, say, persistent objects which we imported, then that would be which then were not destroyed when we got rid of the solar system objects. That would be aggregation. So an example of aggregation would be like using a NumPy array you know, if you have instances of NumPy arrays floating around your code, and you have a class which doesn't have one of those NumPy arrays as an attribute, but maybe accesses it somewhere because maybe it's a global variable or something it imported, then that's aggregation as opposed to composition. So aggregation implies a weaker relationship than does composition. So this is all all on this slide is quite abstract, but it is nonetheless something I wanted to call out, because if you start diving through like Stack Overflow or anything on object-oriented programming, you might see aggregation used instead of composition. And I want to make sure that everyone knows that aggregation is very similar. It also requires no new syntax. It just implies a slightly different relationship than composition. So as stated, that is it for this set of slides. The composition half went a little quicker than the inheritance half because there was no new syntax. And that's one of the great things about composition. So this concludes slides on object-oriented programming. So are there any questions on what we covered today or Monday?